So now let's talk about, once you have the expected values, you have the observed frequencies, now you could easily find chi-square, right? Once you get your chi-square, how do you compare it to the chi-square distribution? Well, the nice thing is the chi-square distribution looks the same as in the test, as in the goodness of fit test. And so chi-square, it has a wall at 0. It can't be lower than 0. And it has a long positive tail. And when you decide on what your alpha is, that's what it's going to look like. Alpha is always one-tailed in a chi-square distribution. Excuse me. But the question is, how do you find degrees of freedom now that we have rows and columns? Well, the degrees of freedom is really going to be the degrees of freedom for categories times the degrees of freedom for however many populations or samples that represent your populations you have. And that's going to be the number of rows, right, because each category is in a row, minus 1, times the number of columns you have, minus 1. So that's how you find your degrees of freedom when you have more than one population that you're comparing. So what are the conditions for the test of homogeneity? Well, these conditions are going to be very similar to the conditions for goodness of fit testing. So the first thing is each outcome in each population falls into exactly one of a fixed number of categories. Well, the categories are mutually exclusive, just like before, right? You have to be in one or the other. You can't be in two categories at the same time. You can't opt out of being in a category. Also, the category choices must be the same for all populations. So one population has to have, if they have 3 choices, the same 3 choices must be the case for population 2. The second requirement or condition is that you must have independent and random samples. Before, in tests of goodness of fit, we only had this requirement that the sample had to be random because we only had one sample. Now we have multiple samples, and they must be independent of each other. They cannot come from the same pool. All right. So third condition, the expected frequency in each cell is 5 or greater. And that just is the same condition that we had for goodness of fit testing. It's because you want a big enough sample as well as a big enough proportion. And number 4 is not really a condition. It's just so that you know how free you are with chi-square testing. You could have more than 2 categories, and you could have more than 2 populations. So you could have 4 categories and 6 populations, right? So you could have a whole bunch of these different combinations. So you're not restricted to 2 categories and 2 populations. All right, so now let's go on to some examples. Example 1 is just the example we've been using to talk about how to find, how to set up your data and how to find expected values. So I've set this up in an Excel file. This is just exactly the same way we set it up previously. I've just found the row totals as well as the column totals. And now I could start on my hypothesis testing. So first things first, step 1. Our null hypothesis should say something like this, that the proportions of satisfied and unsatisfied people, I guess, adults, for Democrats should be the same as for Republicans. So the proportions of category 1 and 2 of satisfied and unsatisfied, I'll say voters, should be similar for Democrats and Republicans. So the alternative hypothesis is that at least one of those proportions will be different between Democrats and Republicans. All right, step 2. Step 2, we'll just set our alpha to be 0.05. And we know that because we're doing chi-square hypothesis testing, it's one-tailed. Step 3, you might want to draw a chi-squared distribution for yourself or just in your head and sort of color in that alpha part and try to think, okay, I want to find my critical chi-square. In order to find the critical chi-square, I need to find my degrees of freedom. And my degrees of freedom is going to be made up of the degrees of freedom for category, as well as the degree of freedom for population, right? There's two populations, so it's 2 minus 1. And you could also see that as the columns, 2 columns minus 1. You don't count these total columns. Those aren't real columns, nor do you count this total row. And the degrees of freedom for number of categories is we have 2 categories, satisfied and unsatisfied, minus 1, right? And that corresponds perfectly to number of rows, minus 1. And so the degrees of freedom here is going to be this times this, right? So degrees of freedom for category times degrees of freedom for population. And that's just 1. So what's our critical chi-square? Well, that's going to be found by chi-inv. We put in our probability as well as our degrees of freedom. And we find 3.84 is our chi-square, critical chi-square. So we're looking for samples that represent populations, sample chi-squares that are larger than 3.84. So step 4 looks something like this. So in order to find our sample chi-square, what we need to do first is find our expected values. So here we have observed frequency, right? What we need to do is find expected frequency. So I'm just going to copy and paste this down here so we don't have to keep scrolling. I'll also bring this up. And so I'm going to write the table here for observed frequency, but I'm going to create the same table for expected frequency. Although now I have to delete all these guys. Okay, so when I look at my expected frequency, I need to find out what's the general rate and then multiply it by however many, in this case, people I have in that sample. So the general rate of being satisfied is 1,316 divided by 1886. So that's the general rate, and that's about 70%, right? I'm going to take that and multiply that by the total number of Democrats. Now, this part, I want to keep that the same, and I want to keep that in the same column. So I'm going to put a $sign in front of the D to lock down that column. And here I'm going to put a $sign in front of both the D and the 21 in order to lock down this actual cell. Because here's what I'm going to do. I'm going to actually copy and paste that over here. And if I look at this, then what I'm doing is I have this same rate, again, the rate of being satisfied, but now it's multiplied by the number of total Republicans. And then I'm going to take that cell, copy and paste it down here. And here I see that now I have the rate of being unsatisfied. And I need to change this to that. And here I have the rate of being unsatisfied, and I'm going to multiply it by total number of Republicans. So these are my expected frequencies. Notice that the totals still add up to be the same, right? And usually it should. There might be some slight discrepancies, but that will just be because of rounding error. So they should still be pretty close. So now we have observed frequencies as well as expected frequencies. And now I need to figure out my chi-square. My chi-square is going to be made up of observed frequency minus expected frequency squared divided by expected frequency. And I'm going to need to find that for Democrats and Republicans, as well as satisfied and unsatisfied. And then add up all of these cells, right? So I'll say grand total, and I'll put that over here. Okay, so let's find the observed frequency minus the expected frequency squared divided by expected frequency. And I could just copy and paste that here because Excel will just move everything down. Then I can take this, move it over here, because Excel will move everything over to the right. Ta-da! All right, and the grand total for all four of these is going to be 547.18, right? And so my sample chi-square is quite large, right? And so do I reject my null hypothesis? Indeed I do. And we can find the p-value. So here I'll put chi dist in order to find my probability. Here it is. Degrees of freedom is going to be 1. And that is a very, very, very small p-value. So this is a pretty radically different population that we stuck in there. All right, and if you want to put in step 5, you could say reject null. Great. Example 2.